So I'm going to start off with an application of linear algebra called Markov chains. Okay. So we're going to use linear algebra to Markov chain application. Okay, so we're going to have a particular setting, and we're going to model it using linear algebra. So the setting is this: that you have a city, and you have the suburbs surrounding the city, and initially 30% of the population is in the city. Okay, initially 30% of the population is in the city. However, every year, 6% of the city people leave and they go to the suburbs. Okay, but every year, 2% of the suburb people in the suburbs leave the suburbs and come to the city. And so the question is, what happens in the long run? And one way of doing this is to create the following model. So you create something called, you create a vector v that we call our state vector. Okay. So you create something called the state vector. State vector v is going to have two entries, c and s, where c is the percentage of the population in the city, and s is the percentage in the suburbs. Okay, of course, c, s is 1 minus c. Right? And for us, our initial state vector is going to be 0.3, 0.7. Right? 30% in the city, 70% in the suburbs. Okay. And so we want to make some way of describing what happens every year. So in this system, every year, there's this migration that goes on. Right? And so we create what's called a transition matrix. And a transition matrix is going to look like this: 0.94, 0.06, 0.02, 0.98. Okay. Transition matrix. And you see that if we take our transition matrix and multiply it by a state vector, then we're going to get 0.94c plus 0.02s, 0.06c plus 0.98s. Right? And you see that that's what happens after 1 year. Right? If this is the state 1 year, then after 1 year, the new city percentage is going to be 0.94 times c plus 0.02 times s, 0.98s plus 0.06c. Right? So this is the state at the next stage, right? The next year. Right? And so this gives you some way of telling what happens in the long run. Yes, Harrison.
Is that a 2% going into the city or a 7?
That's a 2.
2, okay.
Yeah. Okay. So what this problem of what happens in the long run boils down to is, what is this problem turns out to be the same thing as asking, what is this as n goes to infinity? right? Oh, and I should say, I should start off with this 0.3.7. Okay, so you see that in order to solve this problem, you have to take this matrix and multiply it by itself, n times, and then let n go to infinity, right? Which is, maybe not so, it's not so obvious what happens here, right? What happens as if you multiply this matrix by itself over and over and over? Okay, it turns out that that this limit equals 0.25, 0.75. 0.25 to 0.75. This is what's called. So, in other words, with time, 1/4 of your population is going to be in the city and 3/4 in the suburbs. Okay. And so you should be like, how do you know that? How do you figure that out? Yeah. Put your phone away. Yeah. Put your phone away. That's all right. Okay. So, so you should be wondering, like, how do you figure that out? Why is this? How do you find out that this happens, right? Before we answer that, let me ask the following question. What is A times 0.25, 0.75? What if I take that sort of final state of your city and then I add one more year to it?
I have a question.
Yeah.
So is A the transition matrix?
Yes.
So we're not using the state of the next year? Like, you know how you have A times C, the matrix CS equals that?
Yeah.
So,
That's the next year.
okay.
Right? And so this is what happens after n years.
Okay.
Right?
Okay.
And you let n go to infinity. This is what happens after infinitely many years have passed.
Okay.
Okay. What happens after infinitely many years have passed is this.
Okay.
Or rather, this is the limit of that as n goes to infinity.
Okay.
Okay. Okay, so now I'm saying, what happens if you multiply this thing by A? What will happen? Anyone guess? Okay. 0? Like, suddenly everybody dies? Right, it was the end of times anyway, right? So, no.
The original.
You suddenly turn back time to the very beginning after...
You go half, like they equal each other?
What?
Bottom of that. The two bytes equal each other?
Suddenly turn even? Like
Yes.
Montana? I'm just going to keep on asking.
Would it be the same?
It will be the same. It will be the same, right? Nothing's going to happen, right? Because you've just done infinitely many years, and you're adding one more year. Nothing's going to happen. Okay, so you get the same. Nothing's going to happen. Okay. So this is something called a steady state vector. Steady state vector. Okay, so you should be sort of confused about this, right? Like, well, about this, right? How do you figure out that this thing turns into, as n goes to infinity, you get 0.25, 0.75, right? It's actually, this can be clarified, we can clarify this, so we can clarify this by using a different basis. Okay, so so magically we choose two vectors. U1 is 1, 3, and U2 is -1, 1. Okay, so we choose these two vectors, and the reason we choose them is the following. So notice that that A times U1, well, this U1 is 4 of the steady state vector, right? It's 4 times the steady state vector. So when you multiply it, nothing happens, right? The steady state vector doesn't change. 4 times the steady state vector also is not going to change either, right? So A times U1 is just U1 again. A times U2, if you calculate it, turns out to be 0.92 times U2. Okay, so you just do the calculation. Turns out that when you multiply this guy, you get negative 0.92, which is a multiple of itself. Okay. Yeah, Tanya.
Did you just set the first vector to be the steady state? Is that how it is the steady state?
We did it magically. Yeah,
Okay.
we did it magically. Yeah. So yeah, you should be dissatisfied. Like, where did these guys come from? Okay, and we're not going to explain it. We're not going to explain it until chapter 6. But these are what are called Eigen Vectors. Okay. These are what are called Eigen Vectors. Okay. So chapter 6, we'll talk a lot about Eigen Vectors. Right now, we're just going to pull them out of nowhere. But you can think of it as we pulled the first guy. We got the first guy as a multiple of the steady state vector. That's one good way of thinking about it. The second one, you have no idea. You should have no idea. Okay. So we choose these two vectors, and they've got the great property that when you multiply them by the matrix, by the transition matrix, they don't change, right? Right. This guy just gets multiplied by 1. This guy gets multiplied by 0.92. Okay. So they don't. They basically get stretched or compressed. Okay. So here's the key. If we write this 0.3, 0.7 in terms of U1 and U2, we see that 0.3 and 0.7, 0.3 comma 0.7 actually equals 0.25 U1 minus 0.05 U2. So you can do this. You know, this is like a row reduction problem. But anyway, just take it on faith that this thing turns into this. And then what you see then, if we look at the limit, if we look at a to the n, excuse me, times 0.25 u1 minus 0.05 u2, what happens? What do you see? What happens? A to the n times this thing, times this first part, what will happen to the first part? Nothing, right? You're just going to get 0.25 a to the n u1, but that's just u1. Right? No matter how many times you apply a1, you apply a to u1, u1 doesn't change. Okay, now what about the second part? Well, you get a to the n u2. Well, every time you apply a to the n, every time you apply a to u2, it gets shrunken, right? It gets shrunk by 0.92. It gets multiplied by 0.92. So it gets multiplied by 0.92 n times. Right, so you get 0.92 to the n times u2. Right? So what you see is that if we take the limit as n goes to infinity, well, the second thing vanishes, right? Because as n goes to infinity, this thing is going to go to 0, and we end up with 0.25 of u1. But 0.25 of u1 is 0.25, 0.75. Right. So as n goes to infinity, we end up with 1/4 in the city and 3/4 in the suburbs. Okay. So the moral is, yeah.
So why is U1 and U2 what it is?
Yeah, I said we're not going to explain.
Okay.
Yeah. So you see, this is just an example. Don't worry. You don't have to do this. We're not going to. There's no homework that asks you to do this. What? There's no midterm problem.
Okay, just checking.
Yet that will ask this sort of problem. So you should be asking, like, how do we find vectors that when you multiply them by the matrix only get scaled by a number? Right, that's your real question. Like, how do you find vectors that have this special property that when you multiply them, they get scaled by a number only? Eric. Eric. Yes, Sam. So.
You already knew that, like, you already knew U1, and that's just 4 times the steady state vector, but we did the entire limit, like, using U1 to get the steady state vector. Isn't that like wouldn't you already know what it was? You know what U1 is?
No, because what we have to do is express this guy in terms of U1 and U2. Right, we saw, when you did this, you saw that our initial state was 0.25 times U1, right? So if our initial state changed, then this number would change also, right? And so you'd end up with a different number here. Okay, anyway, that's basically, right. So the moral, so the moral is that sometimes changing your basis vector makes phenomena simpler to understand. Okay, right? If we're just sticking with a normal basis and call this thing 0.3 and 0.7, then multiplying by this matrix is difficult, right? But if we think of this matrix, think of the vector in terms of U1 and U2, then we see what's going to happen. What's going to happen becomes clear, right? Okay. So the point is that changing the vectors, expressing this guy as a linear combination of these other vectors was helpful. Okay. And this is what we call a change of basis. Change of basis. Okay. Okay. So now let's get to the actual material. 3.5, change of coordinate systems. Change of coordinate systems. Okay, so here's a definition. Suppose you have V a vector space. You have B, B1 to Bn, a basis of B. Recall that for each vector in your vector space, there is a unique expression V equals alpha 1 B1 plus alpha 2 B2 plus alpha n Bn of V as a linear combination. As a linear combination of the Bi. So recall that we call the vector alpha 1, alpha 2, to alpha n, the vector of coefficients. We take all those coefficients and we put them in a column vector. We call that vector the coordinate vector of V with respect to the V basis. The coordinate vector of V with respect to the V basis, and we denote it by V in brackets sub B. Okay? Right, so for each vector in your space, it corresponds to a coordinate vector. Okay, so for example, right, just now, we had this vector 0.3, 0.7, right, and it equaled 0.25 of u1 minus 0.05 of u2, right? So the coordinate vector with respect to the u basis is going to be 0.25, negative 0.05. Right? You take your vector, express it as a linear combination, and then use those coefficients as your coordinates. Right? And this is a way of, remember, if you have a basis, this gives you a coordinate system. Right? This gives you a way of putting coordinates on your vectors, and this is it. Okay, right? So you take your vector, you express it as a linear combination, and then you use those guys as your coordinates. Yeah.
And this applies to every basis of the vector space?
Yeah, so if I change my basis, then I'm going to change my coordinate system. Right? So every basis is going to give me a different coordinate system. And some of them will be better and some of them will be worse. This one actually turns out to be good for that matrix. Okay, so yeah. Okay, so let's do an example. Say U1 is 1, 1, 1. U2 is 1, 2, 2. U3 is 2, 3, 4. Okay, so these guys are the U bases. Right. The U basis consists of these three vectors, and I ask you to write down 3, 2, 5. The coordinate vector of 3, 2, 5 with respect to the U basis. Okay, so see if you can do it. Okay, take a minute and figure out what you have to do. Right. How do we determine this? How do we determine this? We've got one vector, we want to express it. We want to get the coordinate vector of this guy with respect to the U basis. This turns out to be something that you've seen before many times. So just think about how you do it. Okay, I don't expect you to do the whole thing, but talk to somebody nearby about what you need to do. What do you have to do to figure this? Okay, somebody tell me, what do we need to do? What do we need to do to figure this out? Joel?
Are you trying to get like a linear combination?
Yeah, right, we want to realize 325 as, some constant times the first guy, plus some constant times the second guy, plus some constant times the third guy. Right? So how do you do that? How do you do that?
make those into reduction.
Yeah, just this, in matrix language, this is the same thing as saying that we want 3, 2, 5 to be the matrix 1, 1, 1, 1, 2, 2, 2, 3, 4 times C1, C2, C3. Right? So it's just solve this. Right? You solve this, and then that will give you your C1, C2, C3, which is what you're looking for. Right? C1, C2, C3 is it. Right? So this guy, this is the vector, the coordinate vector with respect to the u basis. Right? That would be your C1, C2, C3. Okay? Everybody get that? Right? So finding the coordinate vector just boils down to this. Right? You're expressing this guy as a linear combination of these three vectors. Well, that's just you invert this matrix and then multiply on the left by it, or whatever. You do your row reduction and solve for C1, C2, C3. Okay. Question? Okay. Right. And if I ask you for a different basis, why don't you just put that basis here? Right? You put your different basis here, and then that would be it. Okay. Okay. So let me ask you. No. So now let's go on to the next idea. Change of coordinates. Right. Change of coordinates from one basis to another. Okay, right, so just like what Yao said, right, if you've got different bases, you're going to have different coordinate vectors, right? You just have one vector, but you've got multiple ways of expressing it, right, depending on what basis you choose. Okay, so suppose that B and B are both bases of Rn. So you've got these two bases of Rn. Okay. What's the relation between the coordinate vector with respect to one basis and the coordinate vector with respect to the other basis? Right? They're not unrelated. Right? They're not. It's not that this thing has no relation to that thing. Right? Yeah, Mariah.
If the coordinate vector only exists with respect to a certain vector, right?
Yeah.
Okay, so for the same vector.
Yeah. So fix a vector in your space. Fix a vector in Rn. It's got the coordinate vector with respect to one basis, the coordinate vector with respect to another basis. Is there any relation between them? Can anyone see the relation between them? I've got my one vector. Here is its coordinate vector with respect to this basis. I've got another vector. It'll be its coordinate vector with respect to another basis.
It's like the solutions.
The same number of entries.
I have no idea what anybody's saying. John.
Is the coordinate vector the same in a way, the solution of that?
The coordinate vector will be the solution, but the matrix will be different, right? Right here you have the B vectors, and the other one you have the V vectors. Right? So
What is the x vector in this case?
X is just some arbitrary vector. So you take some vector in your space, and I'm wondering, is there some relation between its coordinate vector with respect to the B basis and its coordinate vector with respect to the V basis? Yeah, Ryan.
Does it let you switch between them?
Yeah. So how do you switch? How do you go from one to the other?
Multiply.
Yeah, multiply, that's the answer. That is, right, that's actually the answer, right? V1, V2 to Vn times the, times the coordinate vector with respect to V is x, right? But x is also V1 to Vn times the coordinate vector with respect to V. Right? So, if I take the inverse of the V matrix and multiply that by the V matrix and take that product is what's going to get me from one coordinate system to the other coordinate system. Right? This matrix here gets me from one coordinate system to the other. Right? So this is what we call the transition matrix, or actually for now we call it the change of basis matrix from B to V. Let's call it change of basis because we already called it something else, transition matrix, in this lecture. Okay. Okay. Yeah, and sometimes we'll denote it like this: SBV. So like transition matrix from the B basis to the V basis. Okay. So this product here we're going to denote as S sub B comma V. It goes from the B coordinate system to the V coordinate system. Don't worry about that. I promise you. Okay, so here's an example. Here's an exercise for you. Find change of basis matrix from 5273 to this other basis 3211. Okay, so take a minute or two and see if you can do that. Okay, turn to somebody nearby and talk with them.
Yeah, I'm just gonna get it. Sorry. Oh, okay.
Okay, so let's do it. Somebody tell me how to do it. What do you do?
Inverse of one, like one of the vectors.
Which one? So we're going from B to B prime, right? We want to invert the B prime guy, right?
Yeah.
So you take 3, 2, 1, 1, inverse, multiply that by 5, 2, 7. And that's it. Okay, so if you forget, just think, right? Just think of what you're trying to do. Right? 5, 2, 7, 3, 3, 2, 1, 1. Right? We're trying to go from the B coordinates. Right? We're trying to go from the B coordinates to the B prime coordinates. Right? So then it's clear which one you need to invert. Right? You need to invert this guy and multiply on the left by it. Right? And so you do it, right? And then you get whatever you get. Did somebody finish it? What do you get?
I'm not sure, right? I got 1 minus 1 minus 3.
1 minus 1 minus 2 for the inverse. Minus 2, 3, I think. Right? So you get 1 minus 1 minus 2, 3. Yeah, which turns out, I think, to be 3, 4, negative 4. So this is your transition matrix. Okay. Everybody all right? Anybody have questions about this? Right. So this is, you're going from when we're at Rn, we have the coordinate vector. You go from one coordinate vector in Rn, to another coordinate vector. Now we're going to do something a little bit more complicated. And this almost always this tends to confuse people, so maybe pay attention. General vector spaces. So what happens in the abstract case? Right, it's the same sort of thing, right? In V, an abstract vector space, you have some basis V1 through Vn. And so the same thing, you have the same thing, right? You express you have the coordinate vector, right? So given any vector in your space, we define the coordinate vector with respect to the E basis as C1 through Cn, where V has this unique expression, is uniquely expressed as this linear combination. So it's exactly the same thing as before. Okay, so in fact, why did I write this again? This is the same thing I wrote earlier. Okay, so so let's do some examples. What's different are the examples.
Wait, just as the notation, should it be E is the basis of V?
a basis of V. Yeah, okay. Right, so again, this thing is your V with respect to the E basis. Okay. So for example, if we are in P3, right, polynomials of degree less than 2, to get out a basis, so V is P3, we have a basis 1, 2x, 4x squared minus 2. Okay, and if I say, what is the expression, what is the coordinate vector of x squared with respect to the B basis? What is the, how do you express this guy? What's the coordinate vector of this guy? Well, you do a little bit of work. I'm sure you can figure it out, right? You do a little bit of work. It turns out that it's 1/2, 0, 1/4. Okay. Why? Because x squared, if you do a little bit of work, you see that it's 1/2 of 1 plus 0 times 2x plus 1/4 of 4x squared minus 2. Okay, and that's the unique, that's the only way you can get x squared as a linear combination of these guys. Okay, so you figure that out, you would take these coefficients and use them as the coordinates of your vector. Okay, so what we want to do next is how do you go from from the coordinate vector with respect to one basis to the coordinate vector with respect to another basis if you're dealing with an abstract vector space. Okay, and it turns out to be a little bit tricky. I don't have time to give you the whole thing right now, so I'm just going to do an example. And the example will be sort of mysterious. Like, what, how did that happen? Next time we'll explain how it happens. Okay, but I'll show you, I'll give you an example of how you do it, like the procedure. Okay, so this is maybe bad teaching, but, so here's an example. Going from basis 1, which is your standard basis, 1xx squared, to basis 2, which is 2x, 4x squared minus 2. So I want to do something and make it kind of mysterious for you. Okay. So here's what you do. One, you express the B vectors in terms of the B prime. Okay, so you say, okay, well, 1, I take the first vector here, 1, right? I have 1x and x squared. I'm going to express each of those guys as linear combinations of the other guys. Okay, so this first one is 1 times 1 plus 0 times 2x plus 0 times 4x squared minus 2. X, you see, is going to be 0 of 1 plus 1/2 of 2x plus 0 of 4x x squared minus 2. Right? X squared, as we just saw, is 1/2 plus 0, 1/2 of 1 plus 0 of 2x plus 1/4 of 4x squared minus 2. Okay. So then, part 2, then create a matrix. Create the transition matrix. The transition matrix turns out to be the transpose of the matrix of coefficients here. Okay, so you take the transpose of those entries that I underlined. 0, 1/2, 0, 1/2, 0, 1. Okay, and this turns out to be this is the matrix that transforms the vector with respect to the b basis to the vector with respect to the b prime basis. Okay, and so let me just give you, show you that it sort of works. For example, if we look at 3 plus 2x plus 14x squared, okay, and we look at its coordinate vector with respect to the b basis. What's its coordinate vector with respect to the b basis? Just 3, 2, 14, right? Because the b basis is 1x squared, right? So you get 3, 2, 14, right? And if we want the coordinate vector with respect to the b prime basis, well, we just take this thing. Then the coordinate vector of this with respect to the b prime basis is going to be just this transition matrix. So this is the coordinate vector of this with respect to the b prime basis. Okay, and if you work it out, it turns out to be 10, 1, and 7/2. And if you see, 10 times 1 plus 2x plus 7/2 of 4x squared minus 2 actually is what we hope it is. Right? It actually is 3 plus 2x plus 14x squared. Okay. So this matrix that we got by expressing one basis in terms of the other and then taking the transpose of it is the matrix that gets us from one coordinate system to the other in the abstract vector space. Yeah, Eric.
Should there be 4x squared? Oh yeah, did you see that? Sorry.
Yes.
Oh, there's one below.
7 over 2
7 over 2
4x
times
squared minus
should be 4x squared.
Oh, thank you. Yeah, Linda.
Well, taking the transpose, the coefficients always work.
Yes. Yes. So this should be sort of mysterious. Why is this the right thing? Why is this the right matrix to take? We'll explain that next time.